Hi, so today we'll be looking at Monty Hall problem. So the Monty Hall problem is taken from a popular TV show. I mean, it's given in the textbook, so I'll just talk a little more about that so that you have an intuition. Um, a contestant has to make a choice. There are three doors, right? So a contestant chooses one of these doors. Let's say I'll just name them, and the contestant chooses A, right? So first, the contestant chooses a door. Now, every door, so there is something behind every door. So one door has a car, and the other two doors have goats. And if the contestant chooses one of them, the host of the TV show chooses any other one of them and opens it. So let's say I had chosen A, and the host knows um, which of the door, like behind which of the door there is a car. So let's give it for now that there is a car behind C. So it has a car behind C, all right? What the host does is that if I have chosen A, the host would choose any one of the other two doors that has a goat in it. So let's say he knows that there is a goat behind B. So he'll open B, and now the contestant has two options: door A, door C, and then there is a goat right now. Okay, pretty good. All right, because the door B is open and he knows there is a goat behind it. So now the contestant gets to make another choice, either to stick with it or to go for the other door. So now I opened door A and I know what is in door B. So door B has a goat in it. So then now the choice with me is that should I stick with A or should I go to C? Okay. So that's the other choice. Um, what we would think is that, okay, now we have, so this is the intuition, this is wrong. Okay, so let's just talk about it. That is wrong. Um, there are two doors and both have equal probability of, um, you know, getting a car behind it or a goat behind it. Because there are two outcomes. One of them is favorable. Sorry. One of them is favorable. So the probability of winning a car is half. Well, this is wrong. Why? Let's look at why. So this is exactly what has been discussed in the textbook. So we'll go over why is it wrong. That should we go over to A or should we go to C? Should we stick to A or should we go to C? All right. So the question is, okay. So that's the question now. So let's look at something here. So I'm going to define something in the form of P H given E comma C is equal to P of H and C times P of E given H comma C upon P of E comma C. So here H is called the hypothesis, E is called the evidence, and C is called the context, right? So for our example, what we have been given is that the possible outcomes of the car could be. So let me just write it down again. Um, contestant chose A, then the host chose B. Should I stick or not, right? So here the hypothesis is the car could be behind A or C. We don't know that because the host has chosen C and has opened it, right? Right here, that's what we saw. So the host has already chosen opened B. So now there are two options. Should we stick or not, right? Okay. So how do we do that? We have the hypothesis, evidence, context. The context given is the initial choice that has been made by the contestant. So that is the initial choice. Sorry. Right there. Yeah. So that is the initial choice. That is A. The evidence is the door opened by the host. So that is B. And the hypothesis is that it could be the car could be behind A and B. Just gonna write it with a different color. A and C. Okay. So let's write it down again. Let's write two probabilities first. P of car is in C given the host chose B. And the other one is P of car is in A given host has chosen B. And mind this is after our choice of it being A. So the first probability is of us switching, and the other one is of us staying. Okay. So now what is the probability for both of them? Let's look at the first one. So that will be P of car is in C given P of, let's look at the formula up there. So that is P of car given C times P of host host has chosen B given that car is in C upon P of host. Similarly, the other one. So let me just read it out again for you. We're looking at P of car is in C given the host has chosen B. That is equal to the probability that the car is in C, like actual probability, times the probability that the host has chosen B given that the car was in C upon the probability that the host had chosen B. Okay. So let's look at it from a different perspective. Let's look at the odds. Now, so odds would always be a ratio of both the probabilities, like which of these, what are the odds of getting a head over tails would be 1:1, right? So so always odds would be of the form P of car C upon host B. So these would be the odds of uh, getting the car, or the winning the car, given that we switch. Okay, so that's what we're going to find. So we know that the denominators are the same, right? So let's just get those out first. So P of car C times P of host B given car C upon P of car A times P of host B upon car A. Now, one more factor is that initially when we were placing the car, we know that it's equal probability of the car being in A, B, or C, and that's going to be 1/3, right? So let me just write that down. P of car C is equal to P of car B is equal to P of car A is equal to 1/3. And hence we can just cancel these parts right here, for which we'll have P of host B upon car C upon P of host B upon car A. Right? So we are clear to this. So these are the odds of us winning a car given that we switch. Okay. So let's go forward this. Oh, so one more thing that we need to think about is I had A, B, and C. this was the one that I wanted to win. If I had chosen A, um, and the host showed me B, sorry, let me rephrase that. I had chosen A, right? So A is the winner. If I choose the winner, so if A is the winner, I choose A, then the probability of the host opening B and C is half and half, right? But if I opened, I'll just do this as the one that I opened, right? So if I open either one of them, if I open B and the winner was A, so the car was in A, then the host will have to open C no matter what, right? And if I'd opened C, then there was no way that he was going to open A. So it's going to be one for it as well, right? So the probability that we were trying to find here in the first case was P of host given like P the host chooses B given that the car is in C upon P of host choosing B upon car is in A. Okay, so we are finding that. So I'll just write it down again for you. Okay, so if I had chosen A, I have chosen A. This is something that you need to understand. I had chosen A and the car is in A. What is the probability that the host will open B? That's exactly half, right? Again, I have already chosen A. The host has opened B. Sorry. I have chosen A. What is the probability that the host will open door B? So I'll just write this down again. Okay, so given that the car was in A and I chose A, that is this one. What is the probability that the host will open B? That is exactly half. Okay, and if the car was in C and I had chosen A, so it would be similar to this one, this case, but just the opposite way. So if the car was in, if I had chosen A, chosen C right here, that is in this case it would be A. So if I had chosen the other door, then the probability of him opening B would be 1. And hence it would be 2 times the odds. So the probability of actually winning the car would be twice as much as if I switch, then I stay. Okay, so P of winning given I switch is twice as much as P of sorry. So that's twice as much, 2 times that. Okay, so that's the Monty Hall problem. Again, like something just last to think about. We had the two probabilities that we wrote. That is P of winning the car C, sorry, of switching. That is choosing car C given host B. Host has chosen B. Given that we had earlier chosen A, okay, and the winning car was in A again. So that is what we had done, and both of them choosing car C, that is the switching case, choosing car A, that is the staying case, and we found the probability, and we understood the relation would be simple as the odds of finding them would be P of the host choosing B given that the car was in C. So the car of choice was C for me as the contestant upon P of the host choosing B given that I had chosen A. Okay, and that relied completely on the case that if the car was in A and I chose A, then the probability of the host choosing either one of them would be half. But if I had chosen a completely different one, if I had chosen the other ones, then the host had no other choice but to open the door with the other goat in it. right? So that was the only option he had, and he couldn't choose A. So hence that is the probability uh, that we can find using the odds relation between the two probabilities and understand if the person needs to stay or he needs to switch.